Continuing lines and planes. Here we're asked the equation of a plane passing through 2 points and perpendicular to a given plane. Okay, so let's consider let's say there's the plane of interest. We know it contains 2 points. I think it used what, P0 and P1? Right? There's the normal vector. First, what do we know about this normal vector? It's normal to the plane, so what else do we know about it?
It's perpendicular to the
Can it be perpendicular to a point? So it can't actually be perpendicular to a point because it doesn't have dimensions. Right? It's just a singular point that doesn't have dimensions. But it does have to do with the points. And I saw your hand as well.
Is it orthogonal to the points?
What is it? Okay, it can't be orthogonal to a point.
It's normal to the vector between those 2 points.
But it is orthogonal to that directed line segment. Right, and the direction doesn't matter, right? We're also given another plane. Let's call it pi naught. Call that its normal vector, and we're told that pi is perpendicular to pi naught. What does that tell us?
That the normal vector for pi is orthogonal to the normal vector for pi.
Those two normal vectors have to be orthogonal. And we have normal vector perpendicular to that vector and not. So it has to be perpendicular to both vectors simultaneously. So how would you find n? What operation will give you a vector perpendicular to?
V cross and not and plus n.
And the order doesn't matter. That's how we're going to proceed. No, that's the wrong one. Went the wrong way. Here we go. I'm going to call that vector V. Component form. 2, -4, -2. It's got to factor out a 2. Normal vector for the given plane is what? So our normal vector will be V cross n naught. Remember, because we have a scalar multiple, we can just take the cross product of the two vectors and multiply the result by that scalar. -8 -2 -3 -4 and then -2 minus -6. I can just drop that 2, right? I can also flip the direction. I don't like all those negatives. That's just a personal preference. So I'll take the normal vector to be 10, 7, -4. Then our plane (10x) plus 4y minus 7z plus D, negative A times times the x-coordinate of one of the 2 points. It doesn't matter. I'm going to use P naught. Negative 10 minus 14, it's minus 7 times 2, minus negative 4 times 3 is equal to 0. All right, so the plane that's negative 24, so minus 12, right? Equals 0.
Why is it plus 4y minus 6?
Hmm?
Why is it 10x plus 4y minus 6?
It should be. I looked at the wrong. Somehow I got the 4 and the 7s mixed up. So that should be 7y 4z. But I did do the minus 12 right.
What did you get? Everything's correct.
So negative. So every term is going to be a minus sign in front. The x coordinate for the normal vector times an x coordinate of a point in the plane. I did P naught. So it'd be negative 10 times 1, minus 7 times 2, minus negative 4 times 3. X plus 7y minus 4z minus 12 equal to 0. Five, 5z minus 5, 5. Dash cross color function. Label style. Let me do it this way. And let's change the viewpoint. And then just adjust it a little bit there. That should be good. And there's the plane. Get that X. Yep. Something like that. Plane containing 3 points. So again, let's say that's our plane. We know it has 3 points to it. Let's draw this one more vector over here this time. What do we know about that normal vector?
It would be normal to say, direct line segment P0, P1, and P0, P2.
Right? Or any 2 vectors in the plane. So how would you find n?
Cross those.
And again, the order, once you take the cross product, doesn't matter. Also, whatever directed line segments you use don't matter. As long as you have 2 directed line segments using those 3 points, P0, P1, P2, and obviously the directed line segments can't be the same. So it can't be P0, P1, and then P1, P0. So it has to be 2 different pairs of points. P0, P1, I believe, is the same as last time. And this time, I'm just going to drop the common 2 right away. If I'm not changing directionally magnitude, it doesn't change the fact that it's in the plane. And I'll call that V. P0, P2. For -2, -7. Oh, that sucks. And let's call that U.
Is it 1 negative 2, 1, negative?
No, it should be negative. Again, I just dropped the negative. Right? N is V cross U or U cross V. And what are we going to get? -14 minus 2. -7. No.
Wait, isn't it 14 plus 2?
-1 times -2 and then minus that. Right? -2 times -7 minus -1 times -2.
Oh.
Should be 3 next, which would be -4. Yeah, minus -7. 3. And then -2 minus -8, which is 6. And I'll take that as a third the size. You don't have to get rid of that constant multiple. It will drop out when you simplify the equation of the plane anyway. For x plus y plus 2z now plus d. Negative 4 times 1 minus 1 times 2 minus 2 times 3 looks like it's minus 12 again equals 0.
No, doesn't that matter that when you choose to multiply the vector by?
No, you'll always get negative 12. I mean, I challenge you to actually do it with the other 2 points and verify you will get the exact same thing. Can I see your hand?
Yeah. When you're getting the x, y, and z complements, for the y one, did you make it like -7, -4, or -4 minus -7 to get 3?
It was -1 times 4 minus 1 times -7.
Okay.
I flipped the order because the middle term goes negative. Right, so I just did the cross multiplication in the opposite direction. this is going to change. X plus Y plus 2Z. Everything else is going to stay the same, except I think I'll change the color. What color do I want to use? What color did we use last time for the plane? Oh yeah, their definition of pink. That is apparently light blue. Okay. Sure, we'll go with that. Guess it depends on how it's viewed. Could be light blue. Because the color is changing as I rotate it. Yeah, why not? That looks good. I don't think that's going to be right. No, it is. Perfect. Look at that. That's how you could set up the cross product using Mathematica. And obviously dot product is just dot, two vectors. I think you could also do this. I think that would also be the dot product if you just put a period between them instead. And in your calculator, you do have under menu matrices vectors all the way down C, vector operations. So there's cross product, dot product, norms. That's just a good way to check. Shortest distance between the point and the plane. Right, and remember, that is going to be given by the magnitude of the projection of a directed line segment QP onto the normal vector, where Q is any point on the plane. What's N? Point on the plane. Isn't 002 located on the plane? If X is 0 and Y is 0, then you get 5 times 2 minus 10, which is 0. So that is on the plane. It's probably the easiest point to pick. It's not the only point you could use. In theory, there's an infinite number of points you could use. Directed line segment QP would then be 1 minus 0, 2 minus 0, and 3 minus 2. Right, remember here, P is now the terminal point. Q is the initial. I think I will just use Mathematica here, just to show it off. And define my normal vector. We said it was what, 3, negative 2, 5? I'm going to define V to be the point QP, or the line segment QP. Absolute value of the dot product, V with N, divided by I think it's norm. I'm just going to double check that real quick. Yep, it is norm. Thought so. Divided by norm of N. Let's see what that gives us. Is that what you get when it simplifies? So 38 is, well, it's 2 times 19. Yeah, that's what it would get if it's when it simplifies. Versus if you do it by hand, you don't just do all that. 4 over root 38, which Mathematics decides they want to write that as 2 times root 2 over 19. I don't get it. But they're both acceptable. Okay. Surfaces. All I'm going to do in class is introduce you to the surfaces. I'm not actually going to do any kind of work with them. My quiz and test, you're just going to be asked to do either one of two things. Match an equation to a graph of the surface. So that would be multiple choice. Or identify the surface given the equation. So you have to do some algebra. I'm not going to make you sketch a surface. That's ridiculous. Cylinders. When you hear cylinder, what do you think of? So if I ask you to draw me a cylinder.
Soup can. I'm not doing that.
Yeah, right? Soup can or a soda can. That's what you think of when you think cylinder. That is actually just a special type of cylinder called a right circular cylinder. The formal definition of a cylinder is it's a set of lines parallel to a given line passing through a given curve. All right, we call these cylindrical surfaces or just simply cylinders. The parallel lines are called rulings. All right, so here's your soup can. And here is why I love math. There's a cylinder. That one's really not interesting. That's just sideways. Right, so in that case, the axis is the y-axis, right? It goes through the y-axis instead. But that middle one is interesting. That's a cylinder. And you would never have thought of that as a cylinder, right? Here comes another cool one. That's a cylinder. Oh, wait, so is that. Do you know the reason why the two end ones here are called right circular cylinders?
The rulings are all at right angles to the curve.
To what curve?
The given
Which is what?
the circle.
Yes. Right circular cylinder because your base is a circle and extends, the sides extend upwards perpendicular. Right? Or in the case of the y-axis, they extend across, right? They extend horizontally, but either way, it's perpendicular to the base, which is a circle. We also have spheres, which don't have a slide for it here, but I think it is in the lecture video for vectors in space. Right, but standard equation of a sphere is the same as a circle, you just add on the z component. And if it's centered at the origin, it's x squared plus y squared plus z squared equals r squared. Quadric surfaces. These are extensions of conic sections. So quadric surfaces any surface that has that form. So a standard 3-variable quadratic. And obviously all of the A through K, they're all just some constants. There are 6 special ones. Ellipsoid. X squared over y squared plus y squared over b squared plus z squared over c squared is equal to 1. In the case of A, B, and C all being the same, this is a sphere. Hyperboloid of one sheet. X squared over a squared plus y squared over b squared plus, not plus, minus z squared over c squared equal to 1. The axis of this hyperboloid, right? So what is it extending along? Corresponds to the negative, right? So in this case, it's minus z squared, so it extends along the z-axis. Hyperboloid of 2 sheets. Z squared minus c squared minus x squared over a squared minus y squared over b squared equal to 1. In this case, the axis is the positive variable. Elliptic cone, x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 0. And its axis is the negative. Elliptic paraboloid, z equals x squared over a squared plus y squared over b squared. Its axis is the variable that has the single power. And finally, we have the hyperbolic paraboloid. Z equals x squared over a squared minus y squared over b squared. Axis is the single power variable. And notice the axis that the saddle's kind of sitting on corresponds to the positive quadratic. And so it's enclosing the x-axis in this case. And notice it's like avoiding the y-axis. And that's all I want to do with surfaces. With the exception of maybe a week in Calc 2, everything you've worked in or everything you've done has been in what's called Cartesian coordinates, also known as rectangular, xy or xyz. Calc 2, like I said, for that 1 week, you learned a different coordinate system, polar. Which is a two-dimensional coordinate system. We're no longer in 2 dimensions. We're going to study 2 3-dimensional coordinate systems. First one is cylindrical. And these coordinate systems are going to be extremely important, polar, cylindrical, and the third one when we look at multiple integration. So if you don't remember polar coordinates, you have probably about a month to review and get comfortable with it before we start using it. In the cylindrical coordinate system, point in space is represented by the ordered triple r, theta, z. The ordered pair r, theta are just your standard coordinates from polar. And z is your standard z coordinate in Cartesian. All right, so you have a point, x, y, z, which means it is the point that is z units above the point xy in the xy plane. So its projection would just be the point xy. So just look at that projection. What does r represent?
Radius
What do you mean by radius?
from the origin
To,
to the point.
it's the distance from the origin to the point. What's theta?
The direction of the origin to the point.
What do you mean by direction?
Well,
It's the angle
Angle between what?
between the point and origin.
Points can't have an angle because again, it's just non-dimensional.
It's the angle of the spectrum XY plane from the origin to the projection of the point.
I think how you're doing it is correct. You're just saying it wrong.
The angle of the vector going from the origin to the XY component of the point.
Again, I think you know what it is. You're just not saying it the right way.
the angle from the x-axis between the point and the origin.
Be more specific.
Opposite x-axis.
And the line segment, OP, which is what I think you were getting at. And it is important that theta is being measured from the positive x-axis. Theoretically, there's no restriction on r, which I hate. So r can be negative, theoretically. I don't like that. I never use negative r. I always keep r to be positive. And there's no restriction on theta. As long as it's being measured from the positive x-axis, it doesn't matter what theta is. So you, again, theoretically have an infinite number of thetas for any given point, right? Because you have all the coterminal angles. For the most part, we keep theta to be between 0 and 2 pi. And that will change depending on the situation. Now for my favorite coordinate system. which is, by the way, the coordinate system we should always be working in. Spherical.
Why is that?
So glad you asked. So in everyday physics, you're driving down the road, right? Is the road flat? Is it?
Practical purposes,
Is it?
general.
Yeah.
It's on the Earth, isn't it? The Earth isn't flat. So why are we using Cartesian coordinates?
Small approximation.
It better be very small. Let's go further. Fabric of space-time, which is what the entire universe consists of, has been proven to be spherical. So even the fabric of space-time is not flat. Quantum mechanics, you're dealing with atoms. Atoms aren't flat. Nothing is flat.
So could you circumnavigate the universe?
No. Because it may be spherical, but it's infinite radius. Which means what we say is it's just curved. But all of general relativity is done in spherical coordinates because it's curved. And it is a pain to work with. In the spherical coordinate system, point in space is now represented by the ordered triple rho, theta, phi. Rho is the distance from the origin to the point. Theta is the same angle that is used in cylindrical coordinates. Phi is the angle formed by the positive z-axis and the line segment OP. Right, so phi is also called the angle of declination. So rho, not too bad. Theta, easy to figure out, right? Just look at this projection on the xy plane, angle, that line segment from the origin to that projection makes with positive x-axis. Phi is the new concept. How much does it decline from the positive z-axis? Theta, again, typically we take the between 0 and 2 pi. Phi actually does have a set domain. What do you think the domain of phi is? So what would the lowest possible value of phi be? Oh, I've got the silence you.
0.
0, right? If the point's actually on the z-axis, it has no declination. What's the largest value? In radians?
Pi.
Not pi thirds. Pi halves. Why do you say pi halves is the largest? So if it was pi halves, where would the point be located?
Y-axis.
Not necessarily just the y-axis. Right, it's going to be somewhere on the xy plane, right? What happens if the point lies below the xy plane?
It's just 0 pi. It can't be negative. It's only positive axis. So
Well, be careful. Because all the negative represents the direction. Right, so it'd be pi if it's right on the negative z-axis, right? Because it's being measured from the positive, so if you're down here on the negative z, you're declining by pi radians. Why can't it be larger than pi?
then there's a shorter angle from the z-axis to the direction.
We're over to the left side. Those two angles are the same. Right, we don't measure all the way around. We wouldn't measure all the way around like that. It's going to either go this way or decline to the left. So for phi, we always take phi to be between 0 and pi. 0 to pi over 2 represents you're above the xy plane. Pi over 2 to pi is below the xy plane. 0 means you're on the positive z-axis. Pi means you're on the negative z-axis. And pi over 2 means your point is somewhere on the xy plane only. Which means your z would be 0. Conversions. These are your relations for cylindrical to rectangular and from rectangular to cylindrical. Right, so you have 6 total relations that relate cylindrical and rectangular coordinates. Well, technically, 5. Right, because 2 are the same. And those should require no derivation because they were derived in Calc 2 with polar. You have 6 relations for spherical and rectangular. There's your 3 from spherical to rectangular, and there's your 3 from rectangular to spherical. And these, I believe, are derived in the video. I'll just remind you to be careful with the tangent theta equals y over x. You cannot say that theta is the inverse tangent of y over x. And I believe we went over that. I think that was when the second day, right? It was the very first lecture we had. For cosine of phi, would you be able to just take the inverse cosine of both sides all the time? What's the range for inverse cosine? And what were the values for phi? 0 to pi as well. You can actually just always take the inverse cosine of both sides. So that last relation you could write as phi is the inverse cosine of that whole thing. And we will start converting points tomorrow. So homework due tomorrow. 2 homeworks went up today. They will be due next week. One of them is on lines and planes. The other one's on the surfaces. Project is due next week, and don't forget the quiz will go up tomorrow, and I'll discuss it tomorrow.